Hey everybody. So we're moving on to chapter 3.2, and this is all about polynomial functions. So hopefully you're on the right page. It's page 7 on the course packet for module 3 notes. Anyway, we start with the definition of a polynomial, and it starts off with this really scary looking equation. Like it looks like it's all evil and scary, but it's not too bad. I'm going to try to break it down for you. So first, these guys right here are just numbers. So all of these are real numbers. Okay, so how else can I explain that? So when they say real numbers, a real number is any number on the number line. And so that includes whole numbers, like 2, -5. That includes fractions, 2/3, -23/8, just making some stuff up. That includes the irrational numbers, like square root of 2 or maybe -pi. Yeah, so it includes all sorts of numbers. If you can point to it, then it's a valid number. The reason why they use the subscript here is, for instance, when we're dealing with lines, there's y equals mx plus b, or you have y equals ax squared plus bx plus c. And so notice that before we had been using just a single letter. Whoa. I need to get my Michael Jackson glove so my palm doesn't keep on minimizing the screen. So we've been using letters to represent them, but we run into a dilemma. What if we deal with something that's y equals ax, I'm going to make something up, to the 28th, plus bx to the 27th. All right, I'm going to go get my Michael Jackson glove because I keep on pushing the screen. Be right back. Alrighty, I'm all ready to go. So x to the 27, let me erase that right there. Plus cx to the 26, and we can keep on going, but there's going to be a problem when we get all the way to the end. Okay, so if we get to the end, you're going to end up with zx squared plus, and then the question is, what letter do you give to the x, and what letter do you give to the number that's all by itself? Okay, so that line's in the, let me zoom in. Sorry. All right, so plus what? Because we ran out of letters. So we can't, a polynomial is basically one of these things that goes on and there's no limit to it. It can go on forever. So because of that, we can't just use single letters anymore like A, B, and C. So what they do instead is they just adopt the first letter and they give a subscript. Well, this is the 28 x to the 28, so I'm going to call it A subscript 28. And all that 28 means, it's just the variable, or sorry, not the variable, the number in front of x to the 28. Same thing here. Instead of b, we're not going to call it b anymore. They call it a subscript 27 because it's the number in front of x to the 27. This one, they're going to call it a subscript 26 because it's the number in front of x to the 26. And with that notation, we can go here. This becomes a2 because it's the number in front of x squared. This one becomes a1 because it's in the number in front of x to the 1. And then the one at the end becomes a0 because there's an imaginary x to the 0 right there. X to the 0 is just 1. So if we adopt this notation, it kind of helps us with polynomials that go on forever. So anyway, I'm going to erase this real quick because I need room to kind of expand more on what polynomials are, but I wanted to kind of demystify that the subscript notation. So anyway, erasing all this. Harder to erase than you think. Got to get right on it. All right. So a polynomial, as you probably saw me write down earlier, a polynomial is basically, it's going to be a number times x and then an exponent, plus a number, x, and then an exponent, plus a number, x, and then an exponent. And that keeps on going forever. Well, it doesn't have to, but it can keep going forever. And then eventually, if you keep doing that, you'll get to just a number x to the 1, and then a number by itself. And again, like I mentioned before, it's by itself because it's really x to the 0. There's an imaginary x to the 0 right here. This is x to the 1. So the rules are that these numbers can be any number on the number line, just like I mentioned. Okay. Now the only thing though is that these numbers, the exponents, they're more restrictive. The exponents must be whole numbers. And I'm going to say exponents of x must be whole numbers. And so on the next page, we're going to be going over examples where I'm going to ask you, is this a polynomial, yes or no? And you're going to have to basically look at the equation and you say, is every number in front of x a number on the number line? If it is, you're good. Are the exponents all whole numbers? And if they are, then it's a polynomial. So that's all this ugly equation is trying to do. It's just telling you that it's just x to the exponent plus x to the exponent plus x to the exponent. And if it follows that pattern, it's a polynomial. All right? So just some terminology before we start. Coefficient is the number in front of x. Okay. Now we were using terminology for the coefficients. So for instance, a to the 1 is the number in front of x to the 1. Okay, let me remove all of this stuff out of the way. Okay, so a to the 1 would be the number in front of x to the 1. A2 is the number in front of x squared. And then again, I can make something up, but a to the n is the number in front of x to the n. And we can rephrase that. Instead of saying the number in front of, the number in front, the number in front, I can just say the word coefficient instead. So a1 is the coefficient of x1. a2 is the coefficient of x squared. A to the n is the coefficient of x to the n. Anyway, degree is the largest exponent in the polynomial. We're going to do some examples of that in a bit. The leading term is the term. So if I go back up here, more stuff I need to clarify. Each of these guys here is a term. Anything separated by a plus or minus. So right here, this is a term. This is a term. All of this would be a term. And then same thing here. This would be a term. This would be a term. So a term is the coefficient x to the exponent. Okay, so that is considered a term. Now, the leading term is the term with the largest exponent. Okay, leading coefficient is just the coefficient of the leading term. Okay, and then we have three separate definitions: monomial, binomial, and trinomial. So if you're up with your prefixes, you know what mono, bi, and tri mean. Okay, so a monomial is just a polynomial of one term. That means that all it is literally just this, and that's it. There is nothing else being added or subtracted to it. So examples of this could possibly be 3x. That's an example of a monomial. Or another example could be 2x squared. Or even something as basic as 5. Okay, so those are all examples of monomials. It's just a single term, and that's it. All right, now we go to a binomial. That's a polynomial of two terms. And so a polynomial of two terms, the most famous example of that is mx plus b, just a line. Notice that we have two expressions. You have term 1 and term 2. Right? But it doesn't have to be just that. You can, for instance, I can make up another one. Square root of 2x to the 5th plus, I don't know, pi x cubed. So that's another example of a binomial because it's two terms separated by a plus sign. All right, and then a trinomial is a polynomial of three terms. And so the most famous example of that would be what we talked about on Thursday. It's just ax squared plus bx plus c. That's the most popular trinomial because there's three terms, but it can really be anything. I can put pi x to the 9th minus 3x to the 5th plus 17, because why not? As long as there's three terms, we call it a trinomial. All right? Now, one thing I want you to know about all these is that all of these guys are all polynomials. It's just since they're special, because they're one, two, or three terms, they have special names. What else? Yep. So other than that, though, there's no special name for a thing with four terms. If it has four or more, we just call it a polynomial. But monomials are polynomials, binomials are polynomials, and trinomials are polynomials. Anyway, like I mentioned before, what makes a polynomial? The coefficient is all of the numbers in front, just to reiterate what we were talking about. So all of these guys must be real, which means they cannot be imaginary. So as long as they're on the number line, you're good to go. So for this number and this number, they're good as long as there's no i's. And I'm not going to do that to you in this section. Usually, for the most part, they're going to work out. All right. So the other thing is all exponents must be positive whole numbers. So like I mentioned before, that's supposed to be a box, not a 0. So all of these guys, positive whole numbers are things like 0, 1, 2, 3, 4, and so on. So the exponents are very restricted. They have to be positive whole numbers, 0, 1, 2, 3, 4, so on. So that means that there's no negatives, no negative exponents, no variables in the denominator, because the variable in the denominator, let me write it like this, making something up. So a variable in the denominator, let's say that's a 7, is the same thing as 3x to the negative 7. So a variable in the denominator is the same thing as a negative exponent. That's why we say no variables in the denominator. All right, but other than that, if it meets those two criteria, then the domain of polynomials is really easy. It's always going to be all real numbers. So if I tell you that, hey, this is a polynomial, then you automatically need to know the domain. There's no math required. Oh, it's a polynomial? Okay, the domain is negative infinity to infinity. The graph is smooth. That means that whenever you graph it, of course, Gilbert can't draw smooth. Right? So the graph is smooth. You're never going to see the graph do any kind of sharp turns. Like it's never going to start off curvy and then do a kink like that. It's never going to see that. Also, the graph is continuous because the domain is everything. So that means that you can always trace it without picking up your pencil. There's never going to be any weird cases where the graph, let's say, does something like that. That never happens when you're dealing with polynomials. All right, so let's go to the next page. So determine which of the following are polynomials and state their degree. If not, why is it not a polynomial? So looking at this first expression, you can see the first one's kind of basic. It starts off as x to the minus x to the plus x to the plus All right, so if you look at all of the exponents, okay, here, this last term is really x to the 0. Usually you don't worry about it, but just if you're wondering where's the x for that term. Are all these whole numbers? Yep, 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 yep. All right, I don't know why I put the boxes on the bottom. Anyway, maybe to show that it fits the form. So now I look at all the numbers in front. Are all of these numbers real numbers? And the answer is yes. So then, yes, it's a polynomial. And what degree? Well, the largest exponent is 5. So it's a degree 5 polynomial. All right. Next, if we go to the next one, our first rule is to look at the exponents. So are the exponents whole numbers? Why am I writing it up there? I don't know. So the exponents are these guys right here. This is really, so let me zoom in so I can draw on it better. This is really x to the 1. So my exponents are 3, 2, and 1. Yes, those are whole numbers. Now I look at the numbers in front. Okay, and are those real numbers? So is pi square root of 2, and really it's negative, but I'll just write a 1/4, are all these numbers on the number line? Meaning that, can you point to them? Yeah. If I have a number line, let's say here's 0, here's 1, here's 2, didn't give myself enough room. Here's 3, here's 4. Yeah, pi is about 3.14, so there's pi. Just making a big. Square root of 2 is about 1.414. And 1/4 is about right there. Meaning that they're all on the number line. Yes, pi goes on forever. Yes, square root of 2 goes on forever. But they still have a spot on the number line. All right? And so because those are real numbers, we can say that yes, this is a polynomial. Now on the homework or on an exam, you don't have to show that much work. But I know that a lot of people get confused when they're dealing with the differentiation between real numbers and whole numbers. All right, what about this guy? Well, this one's a little One thing I want to point out is it's not like the others. The others were all expanded. This one, notice that this one is already foiled. Or sorry, factored, not foiled. It comes pre-factored. Right? So what that means is that if you want to see if it's a polynomial or not, you have to expand it. Meaning that you would have to get all that and expand it all out. But that takes forever, especially, if you don't, on an exam, you won't have a computer to help you and you would have to do it all by hand. And that takes forever. So there's a little shortcut. And the shortcut, or a cool idea, is that a polynomial times a polynomial is equal to a polynomial. And that's what we're going to do. It saves from having to expand everything out. Okay? So, looking at this, we're going to start with the 5x. I'll try to use different colors. So, is 5x a polynomial? Well, the exponent is 1. That's a whole number. The number 5, that's a real number. So yes, that's a polynomial. Now I can move on to 2x minus 3. Is that a polynomial? Well, notice the exponents there's an invisible 1 up there. This is really x to the 0. So my exponents are all whole numbers. The numbers in front are all real numbers. So yes, 2x minus 3 is a polynomial. And then I go to the last one, x plus 7. So why am I not including the cubed? I'll explain that later. So first, x plus 7. So x plus 7 is a polynomial. for the same reason that 2x minus 3 is a polynomial. I'll use the blue. So we have a polynomial times a polynomial, and then this is still a polynomial 3 times. That's a polynomial times a polynomial times a polynomial because it's to the third. But that's still a polynomial. So x plus 7, x plus 7, x plus 7. Well, if the first one's a polynomial, then the other two are polynomials. Right? So, looking at that, we can see that this is a polynomial. Because everything is a polynomial. Polynomial times a polynomial times a polynomial is a polynomial. Oh, but now we need to get the degree. So to get the degree, let me shrink everything so I have more room. My cat is resting on my mouse pad, and it's making it hard to type. All right, so the rule for the degree is that when you're multiplying a polynomial times a polynomial, what you do is you add the degree. So polynomial times a polynomial equals a polynomial. We went over that. But as far as the degrees go, it's degree A. Let's say this is degree A. Let's say this is degree B. Then the final polynomial will be degree A plus B. You just add the exponents. Okay? So this first polynomial is degree 1. This because it's to the first degree. This polynomial is degree 1. And this one, since it's 3 times, it's going to be degree 3. So 3 plus, or 1 plus 1 plus 3 is 5. So this is a degree 5 polynomial. All right? In a little bit, we're going to go over how to expand these more. But for now, let's just focus on finding out what the degree is and if it's a polynomial or not. All right. Oop, forgot to click on things. All right. So let's go to this next one. So the first thing you'll notice is this guy right here. We have an x in the denominator. So right off the bat, we know this is not a polynomial. If it's not a polynomial, you don't have to worry about degrees. That reminds me, did I find a degree for number 2? So the degree for this one was degree 3, because that's the largest exponent. Okay. 2 more. This is 7, just a 7 by itself. Now remember, if the number is by itself, there's really an imaginary x to the 0 next to it. And so the exponent is a whole number. That's a real number. So yes, it's a polynomial. And we say that it's of degree 0. Okay. Now the last one, 7x squared minus 8x plus 4 over 3. Now this one, I put the number in the denominator, but just because there's a denominator doesn't mean it's not. It has to be an x in the denominator for it not to work. Because really I can just divide everything by 3. This is 7/3 x squared minus 8/3 x plus 4/3. And so notice that the exponents are all whole numbers, whereas the numbers in front are all numbers on the number line. And so because of that, you'd say, yes, it's a polynomial. And this is a degree 2 polynomial because the largest exponent is 2. All right. So on the homework, they're going to give you some questions like that where they ask you if it is or is not a polynomial. If it is, state the degree. And I think the trickiest one is going to be the pre-factored ones. Because if you really wanted to, you could FOIL the whole thing out. It's just very time consuming. And so the shortcut is just to notice that they're all polynomials. So the final answer is a polynomial. And the degree is just the exponents for each one. The degrees for each one. So I had a degree 1, and if I do x plus 7 3 times, it'll be a degree 3. 3 plus 1 plus 1 is 5. Anyway, so I don't have time to do all 6. What I'm going to do is I'll do the left side, and I'll have y'all do the right side. And then I'll post a video to Canvas showing the right side. So find the leading term of the following polynomials. Remember, a leading term is x to the where you want this guy right here to have the largest exponent. Okay, so that's a leading term. Looking at this first one, it's pretty easy. There's my leading term. And from that, we know that my degree is 5. And we know that the leading coefficient is 4. Okay, so the leading term has a lot of information in it. In real life, if you were to model real life stuff with equations, the leading term has almost all the data in it. There's a formula that models like the tides and stuff, and you can model the tides with a polynomial. And if you're trying to approximate it, all you need is the first couple terms of the polynomial, because those hold most of the information. Anyway, I can nerd out about that, but let's just move on to the next one. All right. So this next one's pretty happy. It's x plus 8 times x minus 2. So they want to find the leading term, but notice that this is pre-factored. Well, luckily we can FOIL it out. It's not too bad. First times first is x squared. Minus 2x plus 8x is plus 6x. And then minus 16. And so my leading term is going to be this guy. And so notice that x squared, that's just the same thing as saying 1x squared. So that means that my degree is 2. And my leading coefficient is 1. Okay? Now the question is, what happens if it's more complicated? Notice the one below it is also pre-factored. And unlike the one above it, x plus 8 times x minus 2 is really easy to do. And so really, you just FOIL it out and figure out what the leading term is. Here, though, it's more complicated because I would have to do 3x minus 1 3 times, and then x squared times x squared plus 4. And that's a lot of work to FOIL. And so again, what we're going to do is we're going to do a shortcut like we did on the top half of the page. All you got to do is we already know what the degree is. All right, let me word it like this. All you got to do is multiply the leading terms from each group. Okay? So if I look at my equation, I have 3 factors. I have this factor, this one 3 times, and this one. All I got to do is find the leading term of each factor. Well, the leading term of 2 is just 2. Okay? This next one, the leading term is 3x. But how many times does it happen? It happens 3 times. So it's going to be 3x cubed. And then finally, the leading term of this next factor is x squared. And that's it. All I did was I multiplied the leading term of each factor, keeping in mind the exponent. If the exponent is something that isn't 1, in this case it was a 3, I got to put it there. Here the exponent was 1, so it's just x squared. So I multiply those out. That's just 2 times 3 times 3 times 3 is 27. And that becomes 54 x to the 5th. And notice that this has a degree of 5, and this has a leading coefficient of 54. All right? And notice it still follows all the rules from before. The degree was 5. Notice that this is degree 2. This one, it's degree 1 3 times. This is degree 0. 0 plus 3 plus 2 gives me 5. So it still follows the same rules as before. But anyway, so that's how you do it whenever it's pre-factored like that. So what I want you to do, and there's 2 examples on the right side, so I really want you to practice that. But anyway, do the 3 on the right, and there'll be a video link on Canvas that shows you how to do that. All right, moving on. This section has a lot of stuff in it. So next we're going to go to a power function. A power function is basically a monomial. And really that's all it is. It's a monomial resembling ax to the n. And I want to show you what's going on. So I'm going to open up Desmos. And here we have this. And this is x squared. Right now it's at 2. And I'm going to raise the exponent. And the exponent is going to go all the way to x to the 20. But it's going to stay the shape of a parabola. I did stuff to kind of artificially make that happen. But it kind of shows what's going on. So I'm going to hit play. And check it out. Okay. So notice that as the exponent increases, the graph kind of flattens out. Now the exponent's decreasing back to x squared. So the exponent's increasing. As the exponent increases, notice that the graph kind of flattens out. So it flattens between -1 and 1. Now that between -1 and 1, that changes depending on what the equation is. So that's kind of bad of me for me to say that. But just know that it flattens. As the exponent increases, let me rewrite how I wrote that. Okay, there's a lot of lag on it, but so it flattens as the exponent increases. Now it never gets completely flat. It looks like it's flat because I'm zoomed out, but if I zoom in, oh, there we go. If I zoom in, you'll notice that it never completely gets flat. It just looks like it is because I'm so zoomed out. All right, so again, when I say flatten, it's not perfectly horizontally flat. It just kind of looks that way if you're zoomed in. Anyway, So that's called an even power function. Even because it looks like, well, it's symmetrical to the y-axis. So if I go back over here, as the exponent increases, the graph flattens between -1 and 1, but notice that it blows up for all other x values. I'm going to put the term blows up. Okay, and the reason for that, like if I say to square a number, and you're constantly squaring something, let me just kind of work this out. Let's say you're squaring. What happens when you square a number that's between -1 and 1? Like if I say square 1/2. Well, 1/2 squared is equal to 1/4. Notice that it got smaller. Whereas if I said 3 squared or 2 squared, that gave me 4, and that's larger. So that's what we mean by flattening. All numbers between -1 and 1 get smaller. They get smaller. Whereas all numbers on the other side, all numbers greater than 1, get larger. And same thing for the other side. They get, and I'm going to put it in quotes, but they get larger in the negative direction. All right, so that's what we're talking about. Anyway, power functions with an even degree resemble a parabola, or x squared, which again is a parabola. Power functions with an odd degree resemble x cubed, which again is this shape. And let me show you those on Desmos. So clicking on this, going, let me pause that. Click on this one, that one, that one. There we go. All right. So this is the odd power functions. So it's not x squared, x to the 4th, x to the 6th. Instead, whoa, well, that's not a power function. What happened here? Ah, I got negative. It's not supposed to do that. I'm sorry. That should have started at 1. There we go. All right. So an odd power function has that S shape to it. Okay. Good stuff. So that's odd power function. And then the even one looks like a parabola. All right. The only difference is that the higher the exponent is, the more it flattens. So to explain that more, let's go back over here. Oh, to finish this off, the leading term of a polynomial will always be a power function. And we're going to need that to know what the graph looks like. All right, but anyway, so what we just explained is that if the degree is odd, for instance, n equals 1, this is just a flat line. Not a flat line, but, whoa, okay. There we go. All right, so that's just y equals x. Here, this is y equals x cubed. Notice that it starts to flatten. And all this is a half parabola up and a half parabola in the other direction. So that's y equals x cubed. Now, as you go off to infinity, Basically, what I mean by off to infinity is x to the 5th, x to the 7th, x to the 9th, x to the 11th, x to the 13th, and so on. All the graph does is it starts to flatten. So the parabola, the bigger the exponent, the more that flattened part looks. And notice that it's really hard to tell the difference between these two. So that's why on the exam, or when we actually do problems in class, I'm usually going to stick to this one and this one. I'm not going to give you x to the 5th, x to the 7th, because trying to graph it, you can't really tell the difference between the two, especially if you're zoomed out. Okay, but notice that this guy is a little more flatter. All right, even degree. Well, we have n equals 2, so this is just y equals x squared. Well, y equals x squared just looks like, oh, let me make it in blue. That's just a parabola. Okay, now y equals x to the 4, that's just a parabola with a little fatter bottom. It will a fatter bottom and it increases a bit faster. Because it looks like it doesn't go straight up, but anyway. So notice that here it gets flatter. And I guess I should change this one to be, I didn't kind of show the fact that it increased faster. So the trade-off between it having a flatter bottom is that it blows up a whole lot quicker. Right? And then again, as you go to infinity, that becomes basically you're so zoomed out that it almost looks like it's flat. And then it goes up real quick. And this would be an example of maybe x to the 6, x to the 8th, x to the 10, x to the 12, and so on. All right? But what I want to notice is that it's really hard to tell the difference between all three of these. If I want you to freehand, which we're going to do toward the end of this section, then how can you tell the difference between this, this, and this? And when you're freehanding, the answer is you can't. So as far as exams go, I stick to just the second one. So as far as sketching goes, freehand sketching, the main three I want you to worry about are if it's degree 1, which is a flat line, or sorry, a straight line, degree 2, which is a parabola, or degree 3, which is the snake figure. You don't have to worry about all the other subtleties between all the others. Right? So anyway, yeah. So that's degree 1. So that's just a line. We have a parabola. And we have a cubic. So focus on these three, and you should be fine. All right. Let me take a quick break, and then I'll finish recording the rest. This is a pretty big section. And we're back. So, page 10 starts off with the end behavior of a polynomial. And we start off with these weird notations that you'll see. You'll see x arrow infinity, x arrow negative infinity. And all that means is that as x gets infinitely larger, in the positive or negative direction. Okay, not really like how I wrote infinitely there. Right, then the graph of the polynomial, so when you're dealing with polynomials, they're only, as you go off forever in one direction, they're going to do one of two things. They're either going to increase forever or decrease forever, and that's it. So when you're dealing with a polynomial, end behavior, I'm going to put, hold on. Okay, so imagine I have a cloud of stuff. Now the cloud of stuff is where you have all your x-intercepts, all your y-intercepts, all your peaks, all your values, all that cool, interesting stuff that polynomials do. Okay? After you're done with all your x-intercepts, y-intercepts, peaks, values, after it's done with all that, the graph kind of doesn't become interesting anymore. It's done. So all it has to do after that is it's either going to go up forever, okay, or it can go down forever. It doesn't have to be in that direction. The up forever can be on this side. The down forever can be on this side. Or it can go up on both sides, or it can go down on both sides. Okay? And so that's what we call the end behavior. The end behavior is what happens after all the interesting stuff is done. What does it do in the end? And in this case, this would be down forever, so that would be the negative infinity on both sides. Okay? So if you zoom out far enough, you're going to see that the graph resembles the leading term. And so the leading term is what tells us the end behavior. So let's look at some examples. On Desmos, I went ahead and typed some stuff up. And so my first graph is x to the fifth minus 3x cubed. Oop, let me hide that. All right, so I have this graph. Let me go ahead and make my x-axis a little narrower. Let's make that between -4 and 4. Okay, so notice that we have peaks. So I have peaks. I have a valley. I have turning points. I have x-intercepts. We're going to go into those later. Now, all of this is what we call the local behavior. This is just the cloud of stuff. Okay? Basically, it's not, and yes, it's important. It determines the shape of our graph. But if I zoom out, and this is where right on the screens, then oh look, it actually zoomed out with me. That was cute. No, oh no, wrong thing zoomed out. My bad. How can I get this to work? Oh, I need to click on the pointer again. Okay. Well, that didn't work. Anyway, so as Gilbert deletes all this stuff, that's my cloud of stuff. Ugh. Hold on. Let me pause it while I erase what I just wrote. Okay, sorry about that. So anyway, all that stuff is the local stuff, but if I zoom out, notice that locally the graph looks nothing like the leading term. The leading term is just x to the fifth, because the expression is x to the fifth minus 3x cubed. And so locally, they look nothing alike. But if I zoom out and just keep zooming out, notice that they start to resemble each other. So if I zoom out to this point, And let me see if it'll let me make this between -5 and 5 again. The graphs start to resemble each other. Okay, now they kind of look alike. And that always happens. So if you zoom in, it looks nothing like its leading term. So if I zoom in, let me go back to the home menu. If I zoom in, the two graphs look nothing alike. But if you zoom out, then the graph starts to look exactly like its leading term. And that's always true. And so that's why the leading term determines the end behavior. So that's x to the x to the fifth example. Let me go back to the home screen. And let me use -10 x to the 10th. So here we have this graph. And here we have -2 x to the 10th. And so, again, locally, within this original region, the two graphs look nothing alike. But if I zoom out, and here you can't really see anything because I'm so zoomed out, but let me change the x to make it really small. Notice that the two graphs start to become similar. And so that's always true. A graph begins to resemble its leading term. And then the last one, I have -4/3 x to the 7th. And notice that they actually look a lot alike if I'm zoomed out. But if I zoom in, they look nothing alike. Okay? So that's a general rule for polynomials, that as you zoom out, the graph begins to resemble the leading term. And as far as leading terms go, there's only 4 different outcomes that can happen. So remember, the degree, if it's even, it's going to look like a parabola. If it's odd, it's going to look like a cubic. So if it's positive, here's my cloud of stuff. Whoa. And remember, when I say stuff, that's where the graph looks, where they don't look anything alike. So these are all your x-intercepts, y-intercepts, peaks and valleys. But after you're done with all that, if it's even and positive for the leading term, the graph is going to look like that. Okay? If it's positive and odd, here's the stuff. The graph is going to look like a cubic. Okay? Same thing here. Here we got stuff. If it's negative, all that happens is the parabola flips downward. And again, stuff. And it just flips about the axis. So in this case, it'll be a cubic that looks like that. And so that determines the end behavior. So when they want you to find the end behavior, all you do is you find the leading term, and based on what the leading term looks like, that will tell you the end behavior of the graph. And just in honor of my one student who did this and makes me laugh, I'm going to put little booties, because she did that a couple years ago, and it made me happy. Anyway, whatever, Gilbert, I know. So I'm going to do these two on the left, and again, I'm going to ask you to do the two on the right. But it says, what's the end behavior of the following polynomials? Okay, so all you got to do when they're looking for end behavior is you find the leading term. Now, if it's expanded, then the leading term is easy. There it is. Done. All right, so now that we found the leading term, what does this look like? Well, notice that it's odd. So it's going to be a cubic, and it's upside down. Oh my God, stop it. So it's a flipped cubic. That means that this graph is going to look like this. Again, there's my stuff. Okay. And On some of the homework, they're going to have pictures where you select a picture that looks like this, or you can think of it as it rises to the left and then it falls to the right. Some of the questions, instead of giving you pictures, they'll put the picture in words. So that means on the right side, the graph's going down. And then on the left side, the graph's going up. So that's what they mean. Okay, so sometimes it'll be straightforward like that. Other times, you're going to have to do a little bit of work. And that's what this next problem has us do. They say, find the end behavior of this graph. In the long run, what's this graph doing? Well, just like we did on the previous page, we're going to have to break it up into factors and figure out what the leading term is. So this gives us -2. Oh my god. Hold on, my finger keeps on. And I'm wearing my Michael Jackson gloves, so I don't know why it keeps doing that. Okay, so I have -2. Here, because that's the leading term. X is the leading term, X is the leading term. So there, it's my leading term, but 3 times. Here's my leading term, and again, 3 times. If I multiply all those together, I get -2x to the 6. So that's my leading term. And notice that this is even. That is flipped. So it's a flipped parabola. My graph is going to look like, well, first there's the cloud of stuff, but it's going to be a flipped parabola. And so if you look at this, notice on both sides it's going down. So you would, if you're dealing with a problem on the homework where it puts it in words, then you would say falling to the left and falling to the right. All right. So again, try the 2 on the right. They're a little bit harder, and I'll post the link to Canvas to show you how to do them, or to see if you did them right. But we got to keep chugging because, long section. All right. So now that we know about the end behavior of a polynomial, what the graph does in the long run, now we're going to focus on the stuff, all the x-intercepts, peaks, and valleys. So first we start with the zeros of a function. So a 0, and we're going to be using this term a lot in this section, is any number r such that f of r equals 0. So a 0 is any number where you plug it in. So you have a function. Okay, and let's say you get a number. You plug it in, and it pops out 0 at the end. So anytime that happens, that is called a 0. Or think of it this way. It's any number where this is true. Okay, so if you plug in an x and you get 0 as your answer, we call the number in general a 0. Okay, another fancy term, depends on the book you're using. Sometimes they'll use roots. Now, you may have noticed that this definition, okay, just happens to be the same thing as an x-intercept. Whenever you have a number, comma 0, that's an x-intercept. And that's true. So a real zero, they elaborate on it, is x-intercepts. The reason why they're finicky is because technically that's not always true. Sometimes you can have an imaginary number and 0 as the y value, and that is not an x-intercept. So because of this, sometimes you can have an imaginary number there, and whenever you do, it's not an x-intercept. Why? Because you can't plot it. You can't plot imaginary numbers. But notice that it still gives 0 as an answer. So that's why we call it a zero of a function. But the zeros that you can see, that you can actually plot on the graph, are always going to be x-intercepts. Now in this class, we're just going to usually deal with the real zeros of a function. We're not going to get too much into the imaginary. I think there's one that does, but it's going to be a bonus question. All right, so anyway, in this class, when you see the word zeros, it'll be relatively safe to think x-intercepts. Cool? So for instance, these next questions, find the zeros of the following polynomials. What are they telling us to find? They're just saying, find the x-intercepts. Okay? And so for these, I guess all four are different, so I'm going to have to work all four of them out. But they want us to find the x-intercept, so let's start. Now, whenever you're looking for an x-intercept, or in this case, a 0, it's always going to be equation equals 0. That's what you're doing. That's the definition of any x-intercept, no matter where you're at. So I'm going to get this equation, and I'm going to set it equal to 0. And notice that this can be factored. What are two numbers that multiply to negative 14 but add to negative 5? Well, those are, so multiply to negative 14, add to negative 5. Those two numbers are negative 7 and positive 2. And so since those are my two numbers, that's my factor. X minus 7, x plus 2 equals 0. So x equals 7, x equals negative 2. So remember, I'm rushing a little bit just because I know this is a long section. But x minus 7 equals 0, x plus 2 equals 0. So x equals 7, and x equals negative 2. So those are your zeros of the function. If you wanted to, you could write them as coordinates. So that would be, oh my god, it's frustrating. 7, 0, negative 2, 0. Right. So in this section, we'll try to spice it up a bit. On the right, you have a problem that's pretty much exactly the same. Instead, though, notice that it's x to the 5th instead of x squared. But all of these have x cubed in common. So since they have x cubed in common, I can factor the x cubed out. And I have x squared minus 10x plus 25. Right? And that's, again, we're finding x-intercept, so that's equal to 0. So I can do the same thing here. I want to find two numbers that multiply to negative 10 but add to 25. So two numbers that multiply to 25. Sorry, I had it backwards. But add to negative 10. And those numbers are -5 and -5. So that means this is going to be x cubed, x minus 5, x minus 5. And so we have our answers. This gives me x cubed equals 0, x minus 5 equals 0, and then another x minus 5 equals 0. And so my answer is x is equal to 0, x is equal to 5, x is equal to 5. So my zeros are going to be 0, 0, 5, 0. Okay? So again, on the homework, sometimes they'll do that. It's just this quadratic. The only pre-step you have to do is notice that they have 3 x's in common, so you can factor them out. Okay? Now we get to the trickiest of the tricky ones, and that's this one. Now this one is a little special. This one you have to factor by grouping. So we notice that there's 2 groups here, and this first group has an x squared in common. Okay. And this gives me an x plus 2. This next group has a minus 25 in common, which leaves me again with x plus 2. So I still have my 2 groups. Right? But if we look at these 2 groups, we notice they both have x plus 2 in common. So that means that I can factor it out. And what's left is x squared minus 25. Okay? So basically, this is my first group. This is my second group. Okay, I probably have to change gloves to another glove. Hold on. I'm going to try something out real quick. So frustrating. All right, this glove I'm wearing now feels more, anyway, well, hopefully it'll work. So anyway, this is actually a nice factor. So this is really the x squared minus 25 is x plus 5, x minus 5. I'm so used to writing not equals because of domain. Right, and we get our, in this case, 3 answers. So this tells me that x plus 2 equals 0, x plus 5 equals 0, x minus 5 equals 0. So x equals -2, x equals -5, and x equals 5. Now, not every cubic, when I say cubic, I mean degree 3. Not every degree 3 problem can be solved this way. But in this section on the homework, if they give it to you, it can be solved this way. They're being nice to you. But yeah, so just giving you a heads up for that one. So now let's move on to this last one. And now, luckily, notice that this is already pre-factored. And since it's pre-factored, I don't have to do anything. So I have 5x equals 0, 2x minus 3 equals 0, and x plus 7 equals 0. Okay, there's 3 x plus 7s, but the inside is just x plus 7. It's just the answer is going to happen 3 different times. So I solve for each one, add the 3, divide by 2, subtract the 7, There we go. So the perks of this is that it's finding the leading term is ugly. Oh, I can't even write with this glove. This is terrible. But it doesn't pick up marks. So finding the leading term is tough, but the x-intercepts are easy. All right, so that's the trade-off that you're making. So anyway, on the homework, when they say find the x-intercepts, that's what they want you to do. Or sorry, when they say find the zeros, they really mean just find the x-intercepts. Now we're almost done. Oh, see, like I said, this is a really long section. But we're almost there. Ugh. You got this, guys. All right. So next comes multiplicity. So the multiplicity of a zero is the number of times an x-intercept occurs. The number of times a zero is a solution of f of x. So it's the number of times the x-intercept occurs. Now the question is, what does that mean? If I'm dealing with a graph, how can an x-intercept, so let's say this is 1, how can an x-intercept occur more than once? Because if a graph crosses it, doesn't it just cross the graph once? Or in this case, if it does this, doesn't it cross it once? Or if it does this, doesn't it cross it once? So what do we mean? And what we mean by that is, since that definition is a little confusing, it's the number of times x minus r is a factor. That's what we mean. So, for instance, in this question up here, in the previous problem, for the cubic one, notice that each factor occurred once. So this means that each one is multiplicity 1. Each factor is of multiplicity 1. Okay, but if I go over here to this example, notice that this happened once, this happened once, but this one happened 3 times. This means that x equals 0 and x equals 3/2 are multiplicity 1. But x equals -7 is multiplicity 3. Okay, if I go to the one above it, notice that -5 happened twice. So in this one, this is multiplicity 2. Whereas 0, 0 happened 3 times. So this one is multiplicity 3. Okay, so the number of times that a number is a factor, that tells you what the multiplicity is. So we're going to go more into that. Okay, so before we go more into that, I'm going to jump to the examples first. No, I better go over this one. Okay, so why do we care about multiplicity? Or why do we care about how many times an x-intercept is a factor? Well, it determines if it's even or if it's odd. Okay, So if it happens 2 or 4 times, so in our class, we're not going to go too much into it. So basically, if it happens 2 times, odd if it happens 1 or 3 times. We're going to keep it to just those. Okay? So the reason why we care about multiplicity is it changes the way the graph looks. Right? I'm taking off the glove. I can't stand it. I'm just going to turn off the screen. Not turn off the screen, but there you go. Touch off. Okay. So if an x-intercept or a 0 happens an even number of times, what happens is the graph will touch the x-axis and bounce off it. It looks like a parabola. One or the other. Okay, so notice that the graph, the book uses the word touch. I like to say bounce because, I don't know, it looks like it's bouncing. The graph touches, or you can say bounces. Okay, so if you're dealing with an x-intercept that happens 2 times, the graph is going to bounce on the axis. If it happens 1 time or 3 times, because those are in this class, that's the only x-intercepts that we're going to worry about, is if it happens 1 or 3 times, then what happens is, if it happens 1 time, the graph is just going to cross it without slowing down. And so this is 1 time. And what the graph does is it crosses without slowing down. No, zoom in. Now it's hard to do this because I don't have touch. There we go. Okay. Now, if it happens 3 times, then the graph does this shape, the cubic shape. And in this class, those are the only things, these are the only 3 cases that we're going to worry about. Does the graph bounce? Or does the graph cross once, where it's a straight line? Or does it cross but have a cubic shape as it crosses? So 1, 2, 3. And of course, the 1 and 3 can be flipped. I just didn't have room to write the flipped versions. Okay. Now, because of their power functions and stuff, you only have to focus on 3. But in theory, the higher the exponent, the more it flattens. So in this class, we're not going to have to worry about this. But if it was like x to the 5th, x to the 6th, x to the 7th, x to the 8th, x to the 9th, things like that, then all that would happen was it would keep the same bounce, so even, odd. The only difference is that it would flatten, just like we talked about earlier. So it just, and then it rises really rapidly. But you don't have to worry about that. The only case of curving that you have to worry about is if it happens 3 times. So I'm giving you a heads up. Cool? So that's the only time. So 1, if the x-intercept happens once, it's going to go straight through. If an x-intercept happens twice, it's going to bounce. If an x-intercept happens 3 times, it's going to look like an x cubed as it crosses. So I can go to Desmos and I can show you. So let me close all these. So let's say I have x minus 2. And so notice that that crosses at 2, 0. And I can make the exponent whatever I want. So if it's 1, notice it goes straight through. If it's 2, it bounces. It's a parabola. If it's 3, it looks like a cubic. 1, 2, 3. 1, 2, 3. And you can go higher. Notice 4 is even, so it's still going to look like a parabola. But notice it flattens compared to the way x squared looked. Same thing with x to the 6th, x to the 8th, x to the 10th. The larger the exponent, it still looks like a parabola, it just flattens. Now, odd, same thing. If it was 5, it still looks like a cubic. It's just flatter. And you can get ridiculous with it. 55, notice it looks really, really flat. Same thing if it was, it looks so flat that it almost looks like a rectangle. But it really isn't. If you zoom in far enough, you will see that, there it is. It eventually curves upward. All right, but anyway. So let's do an example. So we'll start with some happy stuff. If I have f of x equals x squared minus 6x plus 9, I factored it for us. And so x equals 3. Okay, we look at it and we can see that x minus 3 happens twice. So the multiplicity is 2. Since the multiplicity is 2, this 2 is even. Okay, and if it's even, the graph is going to touch. Or if you're like Gilbert, you can say that it bounces. Okay, here's another one that's already factored. Here are all the zeros. So x equals negative 3. Negative 3 is this guy. Notice that the multiplicity is 2. That happens twice. So that's going to touch or bounce. Okay, the 1/2 is this one. Notice that that happens 4 times. The multiplicity is 4. 4 again is even. And so it's going to touch and bounce. I'll just say touch because that's what the book does. It touches, but it's going to be flatter than multiplicity 2. And the final one is the 2. Notice this is a 1 right here. The multiplicity is 1. So the behavior, if I go to 1, if it happens 1 time, it crosses without slowing down. So the behavior is cross without slowing down. And again, it's because that was odd. Odd, and it was 1. If it was 3, it would look like a cubic. All right? Almost done. Page 13. Dear God, this is a long section. So, turning points of a polynomial. I consider this optional, but the book puts it in almost every single question. But basically, if you're looking at a polynomial and the polynomial is degree n, then that tells you how many times it can churn. There's a limit to how many peaks and valleys it can have. Okay, so if I write an equation and it's a polynomial, there's a limit. It can't have an infinite number of peaks, it can't have an infinite number of valleys. Okay, so if a polynomial is degree n, it's going to have at most n minus 1 turning points. So n minus 1 peaks and, when they say turning points, they mean peaks and valleys. Okay, so what they mean here is whatever number you put here, you're going to subtract 1 to get the number of peaks and valleys. So that means if this was 4, this would be 3. If this was 10, this would be 9. If this was 17, this would be 16. Okay, so it's always one less. And notice that it's at most. So for example, how many times can this equation turn? Or how many peaks and valleys does it have? Okay, well, you look at it, that's degree 4. And so you can have at most one less. Or again, rather than say peaks, valleys, they say at most 3 turning points. Okay. And again, I can go to Desmos. I can graph a degree 4, and it has to have only 3. So here's x to the 4th. Notice that that has 1 turning point. Okay. That has 1 turning point. That has 1, 2, 3 turning points. Okay, so for x to the 4th, it turns out it can only have 1 turning point or 3 turning points. But it can't go over 3. So there's a limit. What that means is that it can have less, but 3 is the max. Right? And now we can also use the same thing to go backwards. If I give you a graph, looking at the graph, I kind of stole these from the internet. But looking at the graph, you can see that we have a valley, we have a peak, and we have a valley. So there's 3 turning points. Well, we're just using the theorem backwards. If there's 3 turning points, this has to be at least degree 4. You add 1 to it. Same thing here. Here we have a peak. Here we have a valley. Here we have a peak. Here we have a valley. Here we have a peak. Here we have a valley. And so this has 6 turning points. And so this is at least degree 7. It has to be. So if they give you the equation, you subtract 1 to get the peaks and valleys. If they give you the graph, you add 1 to get the smallest degree possible that can create the graph. Now the very last thing for this section, I'm going to do this first one, and then I'm going to leave the last page for you all to do on your own. But finally, what they want you to do is to combine everything that we've done in this ginormous section and to piece it together to create a sketch of our graph. Okay? So what we're going to do is we're going to determine the end behavior. And by the way, this is the test question. So frustrating. Okay. You know what? Maybe if I just keep this on my hand. Okay. So anyway, the first thing is to determine the end behavior, which that means we need to find the leading term. Okay. Find the x-intercepts, which we did that a couple pages ago. Determine where it touches, crosses, or flattens at each x-intercept. And so all that is the multiplicity. Determine the maximum number of turning points. That's what we did on the previous page. And then combine all the information to create a sketch. So let's do that. Now this, again, I copy-pasted this from a past exam. So this is literally a question that you could expect to see on the test. Okay, so it says, I notice I forgot to relabel it. I left it as question 1. But let g of x equal this. And our first task is to find the leading term. So if we look at this equation, notice that this is pre-factored. Meaning that the leading term is ugly, but the x-intercepts are going to be nice. So to find the leading term, it's just going to be You find the leading term of each group, which luckily, everything's kind of already there. So the first one is -2. The next one is an x, but remember it happens 2 times. This next one is 2 times. This next one is 3 times. So it happens twice. The other one is x, but it happens 3 times. 2 times again, sorry. The next one is 3x, but it happens 3 times. And the biggest mistake people make is they put a 3 there and they leave it. But it's the entire thing cubed. It's 3x, 3x, 3x. And so if you work all that out, you get, let's see, 3, 4, 5, 6, 7. So you get x to the 7th. And then 27 times 2 is -54. X to the 7th. All right. So now we're going to determine the end behavior. To do that, it's all based on the leading term. We know that this here is odd, and this number is negative. Well, we know that these two parabolas are if it's even. These two are if it's odd. This is a positive parabola. This is a negative. This is a positive. This is a negative. So it has to look like this picture. It can't be any of these three. So that's the end behavior. On the homework, they might write it as rises to the left and falls to the right. Okay. I forgot to erase that. That doesn't apply to what we're doing. So next is to find the x-intercepts. So to find the x-intercepts, I have -2, x minus 6 squared, x plus 4 squared, and 3x minus 2 cubed. Okay, you set that equal to 0. But notice since it's pre-factored, we don't have to do anything. You're already done. You get each factor, and you set it equal to 0. This first one is -2 equals 0. That doesn't make any sense, so we can toss it. This next one is x minus 6 equals 0. You don't have to worry about the squared, because that's just the multiplicity. And so this gives me x equals 6. So that's going to be my x-intercept, x equals 6. The multiplicity is 2. Okay. The next one is the multiplicity is 2 again. I have x plus 4 equals 0. Multiplicity of 2. Now remember, if the multiplicity is 2, it touches. And again, touch is like bounce. It bounces. And then the last one is 3x minus 2 equals 0. I can add the 2, divide by 3. And so for this last one, x equals 2/3. The multiplicity is 3. That crosses, but remember, it crosses since it's 3. It crosses like an x cubed. So we're going to piece all the ideas together. Looking at my graph, I want to create an accurate x scale. What I mean is, don't do this. Don't do that. Okay, that's not accurate. What I mean is start and actually make tick marks for each actual number up to 6. So since my largest x-intercept is 6, I'm going to put 6 tick marks on each side. I'm going to put 6 tick marks on the other side. Okay? And so now I'm going to plot my x-intercepts. My first x-intercept is 6. I have another x-intercept at -4. And I have another x-intercept at 2/3, which would be somewhere right there. Okay? I already know what they're going to do. This is going to touch. This is going to touch. This one is going to cross like a cubic. Okay? Now, if the question is, in what order? Is it going to touch this way? Or is it going to touch this way? Bounce up or bounce down? So to answer that, that's where the end behavior comes in. I know that after all my x-intercepts are done, my graph is going to look like this. Yeah. My graph is going to look like that. Or let me toward it better. There's going to be stuff, which are the x-intercepts. And then it's going to go down that way. So that means that my graph is going to be going upwards up here. And it's going to be going, let me erase all this. It's going to be going downwards over here. So if I'm creating my graph, I know that my graph has to go up. It has to be coming from above here. But it has to touch. Okay, I'm going to wear the glove again. And let's see if it doesn't pick up. How can a wool glove pick up on the screen is what I'd like to know. Anyway, so the graph's coming up here. So it's going to come this way. So I know my graph's coming from above, which means when it touches, it has to touch like this. Then stuff happens. There's no more x-intercepts. I can't cross until I get to the next x-intercept. So I have to be coming from above, but remember that it has to look like a cubic. So a cubic would look like this. Doop, doop. Now I'm down here. I got to go back up and notice that it touches again. But this time I'm from below. So when it touches, it has to look like that. And then finally, I piece everything together and create my final sketch. And there we go. That's a general idea of what the graph looks like. And there's a question like that that's going to be on the test. And it's not any harder than this. It'll be pre-factored. Just have to tell me what the x-intercepts are, what the leading term and end behavior is, and then combine all the information to create a sketch. And that's the hardest part for this section. We culminated every idea up to this point. But I know this was a tough section. There's a lot of stuff in it. So please let me know if you have any questions. But what I want you to do is to work on this next one. Now this next one, you start by factoring x out first. And then you factor by grouping. But I believe you can do it. We did one of it on, there it is, on page 11. That bottom corner one was a factor by grouping problem. So it's like that. It's just combined with all the other stuff we learned. So again, please let me know if you have any questions. I know this was a long section. I thank you for your patience, and have a good one.